let's see. A couple things. So project-wise, people are getting going on those. That's good. We'll have presentations. I've been kind of kicking around how we're going to do that with so many groups, but we'll just reserve enough days at the end of class to have presentations as scheduled. So the last 3 days of class, at least Friday, Monday, Tuesday, those last three we'll do presentations. And actually, it'd probably be good even to get going on Wednesday after Thanksgiving. So any group itching to go first? Some people do like to go early. Any group considering, if we started them on Wednesday, would anybody be ready? Anybody possibly be ready? And want to go? Not close over there. Some discussion, maybe. All right, let me know. It'd be nice to kind of get maybe 1 or 2 groups done on Wednesday, and that will give us a little bit of time. I want to reserve a bit of time on the very last day of class, talk about the final, do all that kind of stuff. So we'll see how that goes. All right. But the memo report is still due Friday after break. Okay, here's where we were. We've been going through a methodology of how to analyze a central composite or box banking design. These are called response surface methods. So this is using linear regression as our analysis tool, but the complication with having a non-orthogonal design. So how do we go through that? And dealing with the multiple testing problem. So we had our procedure is fitting the full quadratic model, looking for outliers. If that looks good, then the next step would be to reduce the model down to only significant terms. And we did that in 2 steps. The first step was we looked at entire variables with all their terms, and we did an F test that looked at, okay, when we drop all those terms, how much did the SSE increase? And we had 2 variances. The variance that was explained by those drop terms divided by the variance of the full model, and depending on the results of those, either we could drop all those terms, that M number of terms, or we had to keep them in the model. So we go through that for all the variables, and we recognize that visually we can speed things up by not testing every variable. If we see a very obvious term in there that's really significant, we just leave it. We just kind of bypass that step and go on to other variables. So we look at each variable, then we look at each term. So once we have all the variables tested that are candidates, we look at each individual term. We drop the least significant term, run the regression again, look at the results, then drop the next least significant term, run the regression again, until we're down to something like this, in which we have, not that, something like this, in which we have all terms are significant in the model. So that's where we left off. And we said, now we have a reduced model, everything's significant, and the next step is to see if this model works. So very similar to what we did in full factorials. When we got down to our linear model with only significant terms, what we did then was we did a curvature test, right? And so the curvature test was a lack of fit test, or a test of model adequacy. Was the linear model the right model, or do we need to add some complexity to it? So now we're going to look at, well, what's a more general approach for a lack of fit test? So if we think about, let's say we have a line and we have some data points there, and we recognize that our SSE was based on, and our S squared is based on how far away that model right there was from each data point, right? And we said an adequate model would get close enough through the data points. So there wouldn't be any trend left in there. It'd describe all the trend, none of the noise. But we don't really define, well, what do we mean by close enough through all the data points? And so what we're going to do is try to figure out how to quantify that. How close is close enough? And so what we're going to do to base this on is say, well, the model should get about as close to each data point as you would expect, say, if you took repeats at that data point, how close would those be clustered together? So we're going to use that as our measuring stick. So we're going to look at, if I have replicates, and my replicates are, right around here, if I have all these replicates there, and I'd say, oh, okay, my model seems to go through this range of where the replicates are at. That's pretty good. If my replicates, however, were real clustered about this guy very tightly, and my model here was far away from that, I would say, oh, based on that level of noise in the replicates, I think my model should have gotten closer to them. Does that make sense? Okay, so our yardstick here is going to be based on, all right, what is the noise of our replicates? So what we're going to do is we're going to look and say, okay, I've got as I've drawn this, kind of a crazy design, but as I've drawn this, I've got replicates here, and I've got replicates there. Let's go through and, I can calculate an S squared from these replicates. I can calculate one from these. I could pool them together based on degrees of freedom, know how to do that. And so I could go through all the replicates and get one estimate of S squared, and I'll call that pure error. And so that thing will be from wherever I have replicates. Then what I can do is, if I have one thing, if I have a variance of pure error, well, let me do it right. And I could compare that with my total variance that I get from my regression, right? I do this regression, I get S squared equals SSE divided by N minus C, and I could put that in the numerator of this F test. I could, but we don't. So there's one weakness of doing this here. So whenever we're trying to think up or develop a test, we want to make the test as sensitive as possible, right? So notice one thing. If we do this, because remember we have the regression, we have this number. Does everyone agree with that? So if we do this, this number includes the variance of the replicates themselves. Does everyone see that? When I do this S squared SSE divided by N minus C, it's adding up the distance of all those replicates. Those are included in this number. So if I want the most sensitive test, I'd like these things to be totally separate. I'd like to take this top number here and subtract out the contribution of the bottom number, so I have two separate and distinct things. Does that make sense? Okay, so it's a pretty straight thing to do. What we're going to do is we're going to figure out how to do that, and I'll call that the lack of fit, and this is just going to be the S squared minus the S, well, I'm not going to write a formula. We're going to take the total variance, we're going to subtract out the contribution of the replicates, so we only have the stuff that's left over. And so that's called the lack of fit. So it's going to be our total SSE minus the SSE of pure error, and then we're going to partition out the degrees of freedom and get that together. Is everyone okay with that? Okay, so in your notes, I explained step by step. I'll just try to do it a bit differently. It's kind of one of the things try to do is explain things different ways, and hopefully one of them makes sense and you can grab onto it and use it. So this is just a little bit of a development from your notes. So we could think of the total S squared. We have it SSE divided by n minus c, and we're going to get this number. We're going to do the regression. This number is easy to get. And we're just going to say, well, we're going to take that number, we're going to say it's a pooled variance from, well, I'll write it this way. We've got S squared of pure error plus the S squared of everything else. And if we pool those, just like we have before, based on degrees of freedom, I think this is an easier way to think about this, is the regression S squared that we get is just a combination, a pooled variance of the variance we calculate from the replicates and everything else. So let's just think about it in those terms. These are from replicates, and we may in fact have to pool the different places we have replicates to get that guy, and this is everything else. So our process is, we get this easily from regression, then this is pretty easy to calculate, and we're going to use this equation to solve for these things. Degrees of freedom are going to partition, as you'd expect, the total degrees of freedom from the pure error, and the degrees of freedom of your lack of fit. So again, we're going to get this, then we're going to calculate this, then we're going to solve for that, then we're going to go up here, and once we have calculated the variance of the replicates, then we can solve for the variance in the lack of fit, or the everything else part. And then we can do our F-test. The one that we want to do is going to be the variances of everything but replicates divided by the variance of the replicates. And if our model's good, these things should be about the same. That's saying the model should get about as close to those points as the replicates are close to each other. If our model's no good, then this top guy is going to be big, right? Our model's going to be far away from our points, much farther than the replicates are in proximity to each other. Is everyone okay with that? Conceptually? Okay, in your notes, I go through a lot of, here's degrees of freedom and they partition, and here's SSE and how it partitions. It's the same thing as this. I think this, I don't know, over the years I've started thinking about teaching it more and more like this, and so I think it's easier to handle that way. So, but it is equivalent to what I've written here. I think there's just a little bit more jargon and terminology in this. So let's look at this. Let's look at this design. We've got two blocks. We've got an X1 and X2. Looks like a central composite design. We've got at least some alphas in there, and we've got center points. So if we want to do this test, and we'll just do all this stuff by hand. the first thing that we recognize is we've got an SSE from our regression that has 8 degrees of freedom, right? So this would be n minus c. Okay, so let's look at this. So if we think of this thing as the pooled variance between replicates and lack of fit, and we have from our regression already, we've got 25.54 divided by 8, so it's sort of given to us. So now, what do we have? We need to get the rest of this stuff. So first of all, we have total degrees of freedom just sort of given to us as 8, and that's equal to how many degrees of freedom in the replicates and the everything else. So let's look at the replicates. Where do we have replicates? We have them here. Whoops. We have 3 replicates in block 1, 3 replicates in block 2. So the first thing that I'd like to do is I could get what's the variance of those replicates. I'm going to keep them in separate blocks because there might be, if there's a block effect, I don't want that to mess this up. So even in this variance of the pure error, I'm going to get one estimate there and one estimate there, and I'm going to pool those together. So for the top one, I'm going to say, so there's the average of those points. So for the top one, we're going to say we have 2 degrees of freedom times s squared of kind of those top ones there, plus we have 2 degrees of freedom times s squared of those bottom ones there, divided by 4. So what's this? So here we have s squared at the top is, we just have 74 minus 0.7 minus 74.9 squared plus 76.8 minus 74.9 squared plus that guy. 73.2 minus the mean squared, added up, divided by 2. So we add all these up, divide by 2, and I have my calculator. $3.25, anybody get that? So everyone agree that would be the variance of these 3 data points. They're replicates, so we can calculate an average and a variance from them. Everyone okay with that part right there? All right, so why don't you take a minute and do the same for the bottom. So find the S squared of these where we have replicates there. Gonna get a number? 5.52? So we have replicates in 2 places, and we're pooling them together based on weighting them with their degrees of freedom to get an overall variance of the replicates in everywhere we have replicates. When you put that together, what do you get? 4.39, which is what we got, where we got that number there. Any questions on how we do this? If we had replicates elsewhere, well, we just add more terms and pool them all together. So that's the variance that we say, here's the variance of individual measurements, and we have real replicates, so that's a really good estimate of the variance of individual measurements. And now we say, well, our regression also estimates the variance and how close it gets to points. Let's see if that works as well. So, and we have degrees of freedom of our pure error is 4. So therefore we can say degrees of freedom total given to us by regression equals degrees of freedom of pure error plus everything else. So by subtraction, we get the degrees of freedom in everything else. All right, so we got that. So we got this. We know this is 4. We know that's 4. 4, that's 4. We have this calculated. We have that calculated. We just got to put it in there and solve for that. So why don't we do that? It was something like 25.54 divided by 8 equals, we had 4.39 for S squared of pure error times 4 . Anyone get 2? Looks like we should get 2. All right. Any questions on how we got that? So we have 2 estimates of variance. We have, so H naught would be the sigma squared of lack of fit is less than or equal to the sigma squared of pure error. And H1 would be the sigma squared of lack of fit is bigger than that of pure error. And this would be model is okay. Model is not adequate. So we get an F of 0.46. So it's strange, right? F is less than 1 even. So you know it's going to be okay. We can compare that to our F star. F star is how many degrees of freedom in the top number? 4. How many degrees of freedom in the bottom number? 4. Alpha is 0.05. And it's a one-sided test, so you can look up your critical value at 6.39. So what's our conclusion? Is the model okay or not? Model looks fine, right? So we fail to reject the null hypothesis that the model's okay. Any questions on that? Okay, why don't we do a group problem then? So notice we have a data set, just x versus y, a linear regression, and so we have a model, and we're looking at trying to partition this we're going to take the variance that we've got from the total SSE divided by n minus c and partition it. So we need to do a couple things. We need to recognize in the regression output, where do we get that? Where do we get SSE? Where do we get degrees of freedom? All that fun stuff from Excel regression. And then we need to look at where do we have replicates and how do we get a variance of all the replicates together. So. All right, so go ahead and get in groups, work together, talk with each other. Anyone having trouble getting started? Okay, good.
Not sure where to start.
Okay, so first would be to kind of identify in here, where do you have s squared?
Is that from Nova stuff, the SS?
Yeah, you can get it a couple places. So that's s.
Okay.
So you could square that. S squared is there. There's SSE. There's n minus c. So you can get it several places. So then this part's done. You've got this. Then the next part is look at, okay, where do I have replicates? So they come in pairs here. You know, you can get a variance from this pair, from this one, from this one, from this one, from this one, and pool all those together, and that's going to be your variance of all the replicates.
Okay.
Got it? Great. All right. Questions? Yep.
Total degrees of freedom, correct?
How many data points? Are there 10 data points?
Data points, yeah.
10 data points, so it's always, so n minus c, so figure out how many coefficients are in your model. You can see your output there. So as a review, to figure out, that's s, you could square to get s squared. That is s squared. That's SSE. That's n minus c. That's n. C is 2. So you have one of those things right there. The variance from the regression is 14.75. And we're going to take that and we're going to break that apart. We're going to say that is a pooled variance due to just the replicates and then the everything else. So next step would be find the s squared of your variance. You have replicates there. You have 5 sets of replicates. So we need to take those pairs of data and find 5 estimates of variance from those and put them together. Got it? Great. Questions? Okay. Did you guys get for those 5 estimates of S squared at those at those areas of repeats? You didn't get 1.2. All right, that's the variance that you get from pure error. So now we want to take that and say we have a total variance of 14.75. So we want to subtract that out. How many degrees of freedom in that? How many degrees of freedom do we get in here? Good. Right there, 5. So there we have 5. So then how many degrees of freedom in the everything else part, the lack of fit? We have 8 degrees of freedom total, minus 5, so there are 3 degrees of freedom left over. And we get a lack of fit variance, 37.33. That's pretty big compared to that. How many degrees of freedom in the numerator? 3. Good. In the denominator? 5. Alpha's 0.05. Got a 5.41. Rewrite this so we can read it. So this is much bigger than our critical. So is the model good or not? No, it has a lot, there's a lot more variance in there in the lack of fit compared to where we have replicates, right? So you think of the replicates are real close together, whatever they look like, and the model isn't going through those very well. So these distances are very big compared to how tightly the replicates are grouped together. Okay, so let's look at any questions. Let's look at an example. I'm gonna jump over this part of the notes. Although it is kind of nice. Anyway, let's just go over this. It's kind of nice to see those lambdas in there and remind you of diffie-q. Not so nice. Okay. This is just a review of what we've done before. When we want to make model predictions, we use that same equation that we had before, and the point is to try to find x naught, your vector, as to where you're taking your data. And so this was just an example of that. It looks like that polypropylene pyrolysis example that we used before. Find out your x naught, which is based on your model terms, right? So that's the intercept. There, x1. This is just saying these are the coded values. So you go from uncoded to coded. So that's coded, that's coded. So for our x1, for our x naught vector, where do you want to make a prediction? Intercept, we have the placeholder of 1. x1, we want it at 0. There's x2. There's the x1 squared term. There's the x2 squared term. And there's the x1, x2, but it's written as x2, x1 interaction. You do that, simple math, and you've got your x naught vector. Even though that's review, it's probably worth going over one more time. Does everyone see where we got that? So our model had all these terms, and we're making a prediction at a certain set of x1, x2 values. So we need to know what are these numbers in our x naught matrix, and then we have the x transpose x inverse guy here. Looks like sigma s squared was already multiplied into that, since it's not out here. And we have x naught and x naught transpose, and we just multiply it together. Plus or minus 2 is our error limits. And we can do that at various points and get a plot that looks like this. So we have different x naughts that gives us these different plus or minus 2s error limits, and we can plot those up. So let's look at this example. All right. Well, this is a good place to stop. I don't want to barrel through this example. We'll finish this off next time on Tuesday, a class that will be sparsely populated, it seems. But you get real live interaction with your professor for showing up. How's that for a draw? Not much, apparently. Have a good Thanksgiving if I don't see you between now and then.